Good afternoon, I'm Tracy Shimmield and I'm British Geological Survey Director for the Lyell Centre based on the Heriot Walk campus in Edinburgh. It's my pleasure to be presenting a short talk on mining in the marine environment at this workshop on salvage, decommissioning and wreck removal, which is part of the MASTS annual science meeting. The workshop is hosted by the Society for Underwater Technology, MASTS and the Darcy Thompson Forum. I'm really sorry I cannot be with you today, but I've made this short video of the presentation. So today I'm going to give you some information on mining and the impacts in the marine environment. So what's the challenge? Future development depends on technology, and technology needs metals. We can think about renewable energy, robotics, etc. Metals are required to promote and increase decarbonisation of energy, and I've got an example here, a couple of examples. So we can look at a wind turbine, obviously for renewable energy, and a wind turbine takes 500 kilograms of nickel and 1,000 kilograms of copper. That's 12 times more copper to create 1 kilowatt of energy than conventional power generation. And if we consider electric cars, we're all used to seeing electric cars now on the road. An electric vehicle contains over twice the copper content of an average car, 2 kilometres of copper wiring. And obviously we need metals for batteries in hybrid and fully electric cars. So first of all, I'd like to consider the impacts of land-based mining on the marine environment. And this slide here shows you all the different mines around the world. They're land-based mines, but they discharge mining waste called tailings into the marine environment. Green represents operational, orange represents approved, red closed, and yellow ones that are being considered. This is slightly out of date, but it gives you an idea of the number of mines, land-based mines that are discharging mining waste into the oceans. So what is deep sea mine tailings placement? How do they discharge? Where does this waste go? So essentially what they do is they take the waste left after extracting the metal, and it goes into a deaeration mixed tank to take away the air to make it less buoyant. It's then discharged down a pipe of a minimum of 100 metres depth in the water, and then the tailings are released from the end of the pipe. And essentially what you get is you get a buoyant plume of tailings liquid. You also get fine material depending on the water currents shearing off, and then the majority of the tailings go down a turbulent current and land on the seabed. So essentially, when we're thinking about this, we need to make an assessment of mine waste disposal on the marine, benthic and pelagic marine environment and the benthic and pelagic communities. Also, we need to make an assessment of the chemical toxicity of the sediments, and we do that from obviously sampling from the deep ocean. So again, going to challenges, metal production is carbon intensive. It needs a lot of energy. As a consequence, growth in material demand has a strong correlation with human-induced environmental change. Material demand is pushing us towards the environmental limits of our planet. A more sustainable future will include more from less, reuse, remanufacture and recycling, as well as low carbon extraction and processing of metals from terrestrial ore bodies. And also, and this is a key one, could it include regulated low carbon extraction from high grade ore bodies in the deep ocean? Obviously this is an area that's been discussed and investigated at the moment. So just considering deep sea mining and what are the deep sea mineral resources. So the three main types of actively forming mineral deposits in the deep sea. One, seafloor and massive sulfides. They form on or below the seabed at volcanically active plate boundaries and typically have high concentrations of copper, zinc, lead, silver and gold. We have manganese nodules, and these are the ones most people have commonly heard of, and these are created in depths of greater than 3,000 metres water depth. 95% are contained in the sediment with 5% exposed. And I think a key thing here is that these grow very slowly, 1 to 10 millimetres growth per million years. Then finally we can think about the cobalt-rich ferromanganese crusts. These precipitate on sediment-free rock surfaces and are typically found seamounts ridges to 400 to 7,000 metres depth. And again, they're very slow growing, and 75% grow at 1 to 5 millimetres per million years. So you can see that we've got a different type of minerals, and quite slow growing or very slow growing. So we need to consider that in the impact. So just considering the main distribution of mineral resources, you can see here that the red are the polymetallic sulfides, so where we get gold and silver and zinc and copper, and then the kind of lilac is purpley is the polymetallic nodules, and then the blue is the ferromanganese crusts. And again, you can see here the typical water depths that we find these in. So essentially, to consider the licensing of deep sea mineral resources, so there's 2 locations for mineral exploration. There's the area beyond the limits of national jurisdiction and coastal states' continental shelves. The International Seabed Authority, the ISA, issues exploration contracts for the 3 main resources in areas beyond the limits of national jurisdiction, called ABNJ. And here it gives you an idea where we've got these licenses. This gives you more details about the licenses, the contracts that have been entered into by the ISA. So it's entered into 15-year contracts for exploration of nodules, polymetallic sulfides and cobalt-rich ferromanganese crusts with 22 contractors. 19 of these contracts are for exploration of nodules in the Clarion-Clipperton fracture zone, 17 of them, and then the Central Indian Ocean Basin and the Western Pacific Ocean. So you can see 19 there. There are 7 contracts for exploration for polymetallic sulfides in the Southwest Indian Ridge, Central Indian Ridge and the Mid-Atlantic Ridge, and 5 contracts for exploration for cobalt-rich crusts in the Western Pacific Ocean. So that's essentially giving you an idea of where what contracts have been let and what minerals they're looking for. So looking at possible environmental impacts, what we can see that especially this one's more looking at massive sulfide deposits, and this was a slide actually created by Nautilus Minerals, which were looking at a mine in the EEZ of Papua New Guinea called Solara 1. And essentially you can see it's a complicated situation where you're mining in the seabed and then you have to get the ore to the ship, and then essentially you extract the ore and then you have to discharge any excess water and material back into the marine system. So what are we considering here as potential impacts? If we take the surface, so the vessel on the surface, we've got to think of light, noise, routine discharges, and the possibility of pipe failure. If we look at the midwater system, we have to think about pipe failure, input of material at midwater, input of return water, and input of fine particulate material. And then if we look at the sea floor, at the bottom depth, we've got to think of the removal of ore, which is an habitat disturbance and removal. We've got to think of suspended particulate material and plumes being formed, and again light and noise. So these all have to be considered. Should we mine the deep sea? There's no definitive answer and many challenges to overcome. However, development and technology is helping us explore and understand the deep sea environment. And I can give you some examples here. Obviously, a lot of people at this conference will be working in this area and have a lot more knowledge. So obviously robotic platforms for marine research. We've got AUVs, autonomous underwater vehicles. We've got ROVs, ocean gliders, wave gliders, and we've also got airborne autonomous vehicles. And over the last 5 to 10 years, these have developed massively, and the amount of sensors we can now add to these is giving us more opportunities to understand and explore our environment in the marine sector. So just quickly, unmanned underwater vehicles. I'm sure there's a lot of people at the conference that know more about these than I do, but obviously we have unmanned underwater vehicles, remotely operated robots, and they can survey underwater along defined paths and can go down to several hundreds of metres. We can put various types of sensors on. They have different operating modes, different capabilities and objectives. And then obviously we've got to consider smart buoys. This is just a very basic example of a buoy, but nowadays with the different sensors that we have on, or we have developed and available to us, we can make these quite intelligent and quite complex in the amount they can sense. And thinking of if we ever got to the stage where there was actual mining being undertaken, you could imagine you could have smart buoys that were monitoring the environment round about that mining site. That's a possibility. So should we mine the deep sea? Again, as I said, no definitive answer and many challenges to overcome, although technology is now advancing to allow us at least to be able to investigate and understand our environment a lot more. Current estimates indicate that the deep seabed hosts large quantities of metals, sometimes exceeding land-based mineral reserves. But, and this is really important, accurate resource assessments are unavailable at the moment due to lack of exploration. Not a short-time solution to depleted land-based resources, and likely that mining of some scale will happen in the next 10 years possibly. Science can assist in assessment of impacts and development of mitigation and management plans, and scientific uncertainties remain regarding environmental impact, including impact of plumes generated by extraction and collection. So what are the key questions? Well, the big one is, what are the environmental impacts of deep sea mining, and how long will they exist after mining has ceased? Can we accurately assess the available resource? There's still a lot of work to be done there. Is the carbon footprint lower for metal production of seabed minerals in comparison to land-based minerals? Can we develop low carbon extraction of metals from deep sea mineral resources that are financially and environmentally viable? And can advances, and this is an important one, in technology allow us to minimise or mitigate environmental impacts of deep sea mining? And this is just a final slide to say that the joint group of experts on scientific aspects of marine environmental protection are also looking into this, and I chair the working group 42, impacts of waste and other matter in the marine environment from mining operations, including marine mineral mining. If anybody would like to get in touch with me, I can possibly answer any questions, but I'm very willing to have a discussion more about the work we're doing in Gazamp or any other work. So thank you very much for listening today, and I hope you have a very interesting and good conference. Thank you.